So next we have Dr. James Voogt, who is going to speak to us from on urban heat and community design. Dr. Voogt, or I'm told it's Jamie, we can refer to him as Jamie, is professor and chair in the Department of Geography and Environment at the University of Western Ontario in London, Canada. He's an urban climatologist who specializes in the measurement and modeling of urban surface temperatures. He received his BSc in 1986 from Queen's and MSc and PhD in 89 and 95 from UBC. He's contributed to research projects on understanding the three-dimensional surface temperature of cities, thermal anisotropy over urban areas. I looked that word up last night. I'll ask Jamie to define it later if you like. The use of remotely sensed surface temperatures in urban climate model evaluation, the climate performance of green roofs, and spatial variations in the heat impacts on urban residents. Dr. Voogt is an editorial board member for the journals Remote Sensing of Environment and Anthropocene. He is past president of the International Association for Urban Climate and a co-author of the text Urban Climates, published by Cambridge University Press. So over to Jamie. Thank you.
Thank you. So, the little one, right? I'd like to thank you for having me. It's nice to be back. I spent a lot of time in my PhD driving up and down these streets measuring temperature. So here we are again talking about temperature. I'd like to acknowledge my co-authors, Scott Krahenhoff from Guelph and Ian Stewart, who's at U of T, and we actually all did our PhDs at UBC, and so there's a connection that way. We've done a lot of talking today about buildings, individual buildings, and I'm going to take it up a bit of a scale, and we're going to be interested in not just the building, but how buildings are grouped with other buildings, and if we take it even another scale, if we collect a whole bunch of buildings together, what do we have? We have a city, right? So here's Vancouver, and how does Vancouver impact climate locally? Through the changes that are wrought by urbanization. So what do we have here? We've got changes to the surface cover, we've got changes to the material properties, we've got changes to the form, that's the three-dimensional form of the surface, we've got changes due to the expansion of cities, and all of those relate to the surface of the city itself. Metabolism is a little bit different than the other categories. That's the changes we make more directly to the atmosphere through injections of heat, moisture, and air pollution. So all of those changes together results in or manifest in a change to the surface energy balance, which is really conservation of energy at the surface, and it affects temperature. So these are satellite images of Vancouver by day on the left and night on the right. And you can see that there are large differences of temperature depending on the characteristics of the surface that we saw before. And changes occur not just to the surface, but also into the air. And so we get the famous and the most infamous heat island that's known, that we've known for well over a century now, since the first studies by Luke Howard back in, I think, the early 1800s. We have the air temperature, or sometimes called the canopy layer heat island. And one thing I'd like to point out here is that the canopy layer heat island and the surface heat island that we saw in the image previous, they're quite different by day. So you notice that the city, the temperature differences in the air over the day are not very big, whereas the surface temperature differences are, but at night they're much closer together. So both heat islands are synchronous at night, they're less synchronous by day. So that's something to keep in mind when we're thinking about planning. There's spatial variations of both of those, and we'll talk a little bit about them more and what controls them, but it goes back to those properties of the surface. This is a sort of summary diagram that I took from the recent Intact Insurance report that came out of Waterloo, and they've taken a diagram from the IPCC and modified it a bit. But it does maybe a nice job for a general audience in terms of thinking about what are the contributions to this urban heat that come in different categories. So there's city geometry, we've got heat from human activity, and we've got heat from retaining properties. So that's combining all of those factors on surface cover, built form, and materials. All of those things are generating heat, and they generate heat in different amounts. So those are contributing to our heat islands. And on the other side, we have cooling effects that come from vegetation and from water. And they're coupled again because vegetation is providing some transpirational benefits, so that's latent heat, consuming energy. I've modified it a little bit here by adding some text. So one thing I think I want to point out is that there's been a lot of talk today about cooling of buildings. If you're air conditioning a building, especially during a heat wave, you're dumping heat outside. And if you're dumping heat outside, you're actually increasing the temperature of that outdoor environment, and you're synergistically adding to the change in urban climate that's existing. So that's enhanced during heat waves. I think one of the things cities want to think about is where that heat is being dumped. Is it being dumped at street level? Is it going out the top of the buildings? One thing we've noticed more recently in climatology is that some of the actions that are being used to address heat have a bigger impact on the air layer above buildings, and some actions have more impact in the air layer between the street and the buildings. So you want to think about targeting heat mitigation efforts on the layer in which you need that impact. Water is the other category here that I modified a little bit, and I added a little few red bars on top. So water, in some cases, can actually increase heat in an urban setting. And so if you're talking about small ponds, late in the summer and at night, the heat capacity of water will result in them warming up such that if you have a heat wave and overnight cooling is important for human comfort, those smaller ponds may be contributing to heat at night, not alleviating heat. So you have to put a little bit of, you have to watch the use of water, and we got to be careful on what the temperature of the water is relative to the temperature of the air. So if we think about some of these parameters in a little more detail, this is a picture of Toronto. I like getting the window seat on the plane, so I'm always taking pictures. And near Markham here, we can see some distinctly different parts of surface cover in a city. So really distinct changes here in impervious versus vegetative cover. And I can also outline this area a little bit to also try to give you a sense of one of the things that climatologists like to do is talk about local climate zones. And those are basically a way that urban climate scientists can think about neighborhoods that have properties that together give them a different temperature than other neighborhoods. So this area is a distinct local climate zone based on its properties, and the areas around it are going to be a local climate zone with some different properties. If we think about surface cover and impervious versus vegetative fraction, basically the more vegetation we have, the more energy we're going to put into latent heat versus sensible heat, so that's a cooling effect, whereas the opposite is true if we're adding the impervious surface fraction, we're going to be sending more heat into the air, so sensible, that's going to heat the air the opposite direction. And those local climate zones I was talking about, they get linked to the heat island. So this is a heat island transect that Ian Stewart had worked on, and it's actually for Vancouver. And the little graphic here depicts, sort of in cartoon form, those different types of urban neighborhoods are linked to the temperature differences. So the reason I wanted to show this is because you don't have to be an urban climate scientist to know something about the urban heat island. You can look at the city characteristics. And this was sort of designed for people in urban planning and in urban design to give them a handle on making that translation between what's a city look like and what's its impact on the environment. So I think it gives us a sort of first order approximation with no other information we can get some sense of where there's going to be heat impacts in a city. If we look in more detail, then the specific properties of a surface are what's going to drive its thermal behavior. So is it open to the sun? What's its orientation? Is it exposed to the sky at night? What's its radiative properties? Is it absorbing sunlight? Can it emit radiation? Is it wet or dry? How well does it conduct and store heat? And how rough is it? So how rough governs how well it will offload heat through convective means. And this is a set of 4 images from Elgin Street in Vancouver, which is Knight Street and 49th, more or less, just a little northwest of that corner. And you can see the progression over time that there's large changes in temperature, both spatially and temporally. And so, for example, if you look at a building roof, which is your interface between the occupants and the building space below, it's really hot by day. It's open to the sun. It probably, in this case, doesn't have a very high solar reflectivity, so it's absorbing lots of sunlight, but it's insulated underneath, so it can't conduct heat, so it gets really hot and it's exchanging heat with the atmosphere above it. Some other dry surfaces I'll point out too, if this works here. The grass. So the grass here, and I think you can see just on the boulevard, there'd been a fairly long drought during this period. One of the hottest surfaces we see during the day here is actually dry grass. So it's pointing out the important control of surface moisture. And at night, that building roof is switched from being the hottest surface we see to being the coldest, as is that dry grass. So that's radiant heat loss at night, so openness to the sky is letting those surfaces cool off. So there's a cooling effect there. I think we got from one of the earlier talks about talking about human health is that heat is more than temperature. And so this is a street canyon, what we like to call a street canyon, the space between 2 buildings bordering a street. This is in Basel, Switzerland. And then a kind of cartoon diagram here showing you across that canyon what the air temperature looks like. And the air temperature variation at this scale it's slight, but it's not very big because the air gets mixed by convection. So the air temperature variation in this canyon is not very big, but the actual temperature that a person would feel based on mean radiant temperature or their physiological equivalent temperature, which is driven by the surface temperatures they feel and the solar loading that they have on this side of the street versus in the shade, are extreme. So if you're interested in thermal comfort on the outside, in the outdoor environment, then the exposure to sunlight becomes really important. And so that street canyon is one of our ways of addressing what urban climate, one of the urban climate controls that exists, right? So what's the spacing of our buildings that we want to have? And that spacing of our buildings is something that's pretty hard to optimize. So I've put down here a recommendation that came from Tim Oak back in 1988 in a paper he wrote, and in our discussions leading up to this conference, we weren't sure we had anything better than this, but so a height to width ratio of buildings of around 0.5 is good in the sense in a mid-latitude climate because it gives us access to the sun during the winter. It provides enough ventilation to disperse pollutants that might accumulate in the canyon. It provides shelter from winter winds, and it also allows us to retain some warmth at night. You can see on the graph on the right here, this is again physiologically equivalent temperature, so the temperature a person would feel in a street canyon. Here's a shallow canyon. You can see in the summer they're going to feel pretty uncomfortable because of all that solar loading. Whereas if in a deep canyon where there's more shading, here's the point at which that canyon is sunlit in the middle of the day, otherwise it stays pretty cool. So the canyon geometry we have for the summer there in that type of climate favors a deep canyon, but it switches in the winter, right? So in the winter, that deep canyon provides shading all day, it's too cool, whereas the more open canyon is more comfortable in this winter. And these are from a dry, arid climate. If we look at night, always the deeper canyon provides relative warmth because that deeper canyon is letting surfaces cool off more slowly. So that's illustrated here. So here's our Basel Street Canyon. On the right, a thermal image showing what it looks like at the end of the night from cooling. You can see that the north side of the street, so this street we're basically looking west. So the north side of that street, you can see the retention of the heat that's accumulated over the day, right? So down here on this side of the street, it's really warm because that's where the sun is being absorbed all through that day. The roofs have become very cold because they are seeing lots of the sky, right? They have a big sky view factor. They're releasing their heat, not so much in the street canyon itself. And so that spacing of the canyons, that height to width ratio, is a very strong, one of the strongest controls we know of for the nighttime heat island. What about the canyon orientation? So if we think again about solar access, if our street canyons are oriented north-south, that's probably better in the warm season for providing shade to keep people comfortable. Whereas if it's oriented east-west, that's going to be better in a cold season based on solar access. But we have to keep in mind what kind of access do we need in terms of the geometry for ventilation. We also have to think about what we were just hearing about before in terms of architecture and design is the prevailing climate. So in more humid climates, ventilation becomes relatively more important in terms of keeping us cool. If we look at particular materials on buildings themselves, a strong control of surface temperature will be the reflectivity of a material, or its albedo for sunlight. And so cool roofs, those that have higher albedo, have the ability to reduce temperatures in cities, and those are commonly implied in many hot environments. The issue with cool roofs is they're generating cooling to the air layer above. They don't necessarily benefit pedestrians at street level. Green roofs are another category of cool roofs. Green roof performance, though, probably not as good as just straight higher albedo. And Adam was talking about selective emitters, which are even better, right? So they're coming sooner. So this is just showing some work we did in London and Halifax that showed relative performance of green roofs. These are surface to air temperature differences, so a frequency distribution. You can see in Halifax, that's a green roof that's performing well because it's got lots of moisture, but even still its performance is in terms of cooling is probably not quite as good as the white membrane roof that it's based on. For road surfaces, this is, and I guess you could apply this to walls as well, talking about thermal materials as a property for keeping the urban areas as a mitigation heat technique. If we increase the storage capacity for heat, we can reduce the daytime peak temperatures, but with the penalty of making the nighttime warmer. So essentially, as we increase the heat capacity of a material, we're going to shift the peak temperature a little bit later in the day, and we're going to cut it down a bit, but we're going to suffer a penalty overnight. So applying that kind of technology is probably better in an environment where your problem is associated with a daytime really hot temperatures, so maybe the Okanagan type environment, whereas if you get into a place where the heat problem is overnight lows, then this is probably not a good idea because it's going to actually add to the burden at night. Vegetation is a really big mitigation technique because it provides shade, transpiration, surfaces for pollutant dispersion. It also provides shelter, and it can also have a negative impact on reduced ventilation. So more vegetation in general is good, but where you want to place it, I think you want to be strategic on tree placement. So a little graphic here, and I've tried to be efficient in my diagram. So if you have an east-west canyon, you want to preferentially put your trees on the north side to try to shade the surfaces that get the most sunlit. And you're already getting shade from the buildings on the south side of the street, so you don't need to put trees there as much. If your canyon is north-south oriented, then my diagram still works because putting trees so that they shade the west-facing walls is going to be your biggest bang for your buck because that's when the maximum daytime surface temperature is occurring. You want to have enough trees that you're going to provide a lot of shade for the surfaces present, but you don't want to fill the street canyon with vegetation because you'll cut down on ventilation, which will be important if it's a humid environment, or it's important if there's pollution in the street canyon. So there's been work shown that you can get to a point of having too much vegetation and the air quality goes down. So we've got to be careful on that. The other choice in terms of vegetation is trees are generally better at providing daytime cooling, whereas if you have ground level vegetation, that provides more cooling at night. And this is a slide that shows a little bit about the vegetation air temperature cooling. So the combination of shading and transpiration provides the total cooling benefit that vegetation provides us. It's about 0.3 of a degree per 0.1 of a fractional cover. So every 10% increase of vegetation cover gives you about 0.3 degrees C of cooling. That's for trees. There's a lot more variability to the performance of vegetation if it's grass or a green roof because of moisture variability. I think there's going to be a talk that's going to talk about equity, but I put this slide in, and this was a figure I got from the Health Canada report. It's from Vancouver, and there was just a recent study that Scott and I were talking about by Ash Broadbent from Arizona State, where they had shown that directing the cooling or heat mitigation strategies to parts of the city that need it the most in terms of equity actually gave them the biggest bang for the buck. So if you have a part of your city that is heat sensitive and has a lot of areas that could be treated, so in the case of Arizona, it was they had a pretty dense neighborhood with a lot of roof area that they could apply high albedo coatings to, and those roofs were also home to a lot of sensitive people. It gave them the biggest cooling performance relative to the treatment area that they provided. So it's not just how much vegetation, but where do you put it and who needs it in order to get your maximum benefits. If we go up a scale, I think we always want to keep in mind what is the topographic or landscape setting of our city. So we can do a lot at the building scale, we can do some at the neighborhood scale, and we can do a little bit at the urban scale, but we also want to don't shoot ourselves in the foot in terms of thinking about the cooling resources that have been provided to us by our natural environment. And so we're in British Columbia. You have a lot more topography than we have in London, Ontario. Cold air sinks. So cold air drainage is something that's always a benefit to think about. So in Europe, they're much better at thinking from planning perspectives of don't block ventilation corridors. So for heat purposes, especially in, say, the Okanagan, cold air drainage is probably a big resource to try to help keep your city cooler through the evening and into the morning hours. In Vancouver, think about the sea breezes that are being generated and don't block off the prevailing sea breeze routes. So ventilation corridors is a very important aspect of urban climate design. One of the take-home messages of urban climate writ large would be doing an urban climatic map analysis is a good idea because that's something the planners can work on, not just for overheating, but it can be used for also ventilation corridors and finding sensitive areas and areas of cool air resource. The overall layout of a city, when we think about climate change, denser is better in terms of carbon emissions, but there's a paradox because as you get too dense, air conditioning generates more heat into the canyons, the pollution concentration is higher, and more dense cities have a higher nighttime heat island. So there's a trade-off there, but perhaps we go back to that height to width ratio of about 0.5 as being an example to be somewhat of an optimum value. Our future urban climates are going to be hotter, but they won't necessarily drive a bigger heat island. So these are results, these are modeling results for Montreal. The columns on the left, so this is meteorological summer, June, July, August, and September, October, November in the fall. The heat island is not necessarily more apparent. This is a surface temperature heat island, but the number of hot days definitely goes up. So one of the concerns is not that the heat island itself gets bigger, but the heat island during heat waves is often seen to be bigger. And so what about adaptation? So what about adaptation in future climates? What should we be doing? What's the perspective for it? So Scott had done some modeling work for the United States. These are results for the Northwest area of their study domain, which is probably more or less reasonable to compare to southern BC. And these are daytime and nighttime results for these are the hottest days. So these are the numbers of hottest days that are going to occur. And this is your moderate warming RCP 4.5 scenario. This is the sort of business as usual, the stronger RCP 8.5. So, and these are different mitigation techniques being applied at the urban scale. The brown bar is all of them combined. And so all of them combined only cuts down less than half of the warming we expect in the worst case scenario. So full adaptation measures at the urban scale provide you some benefit, but mitigation is going to be critical to not having lots of hot days, right? So the difference between this bar and this bar is really large. So here's a summary. Cities create their own microclimates. We want to be cognizant of those. Cities are also really important for large-scale climates because they're driving the greenhouse gas emissions that drive large-scale climates are linked in large part to urban activities. We want to consider a range of heat mitigation techniques across scales. We can probably get up to around 2 to 3 degrees of cooling if they were widely implemented. The type of heat mitigation you're going to do depends on your prevailing climate. So the right answer in Vancouver is not necessarily the right answer in the Okanagan, because one is a dry climate and one's much more humid. Is the problem daytime maximum temperature or nighttime minimum temperature? That also helps guide your design decisions. Trees are almost always a good answer. If you don't have room for trees, think about other ways of shading. Be aware of the topographic setting of your community. There's a cold air out there, make use of it, and develop an urban climate map for your community. So that's it, thank you. I'm just going to show you 2 slides that were books that I used that I think would be good, that provide good resources in terms of thinking about design with climate. Thank you.
Got any questions? Or Matthew, let me know if there's something online. I can start with one if somebody's thinking about something else. I wonder about your comments on the perspective from the research side and seeing how much of this information is being picked up at the city level. Do you find that communication exists and the message is heard, or do you think there are gaps and improvements that could be made to incorporate some of this information?
Yeah, that's a good question. I think in North America, it's a bit climate sensitive. So I think places in, for example, the U.S. Southwest. So I think of cities like Phoenix, maybe Arizona, parts of Arizona, parts of California, where heat is already a problem and it's a problem all the year. They've become more aware. So, cool roofing materials, they cool everything down there, right, is in their lingo. As you move to other parts of North America, I think it's a bit different because we're still a 4-season climate, right? So it's actually a big challenge for design is to have something that works in the summer and doesn't give you too big of a penalty in the winter. I think my own experience working with cities is that they're also interested in things that cost them money. So, for example, green roofs have been popular with cities because they pay for water infrastructure, right? They know that runoff, and they know that climate change with runoff is an issue. So they're often interested in green roofs, but more from a hydrology perspective than a heat perspective. The people who are interested in heat tend to come from the health communities. And so the health community who knows that heat can kill you actually has more traction with policymakers. So I think, one of the reasons I come out and talking to different audiences is that urban climate in a North American context has had less traction elsewhere. And I think to put pressure on policymakers, it takes a bigger tent of people to put that pressure on them. So that pressure needs to come from engineers, it needs to come from health people, it needs to come from educators, right? So the more people that are kind of aware of these things, the more I think that we can make progress. Because at its heart, the urban environment is actually a critical environment because it's where most people are exposed to climate change, and it's also the environment that's feeding back to climate change with greenhouse gas emissions, right? So it's like something like 70% of greenhouse gas emissions are driven by urban activities, so it's a big deal.
Okay. One more time. Thank you.
Thanks.